Hello everyone and welcome to the Flare Builder online workshops session number 8. Trustless insurance market using FDC Web2 connectivity is the name of this workshop. So basically what we'll be doing in today's workshop is we'll take a look at a simple insurance agency built on Flare using FDC, and in this weather agency we'll basically be collecting weather data from a public API to resolve policies. My name is Nik. I'm a DevRel here at Flare, and I hope you enjoy this workshop. So before we start the workshop, let me just tell you that there will be a time slot for Q&A at the end. So please do write your questions in the chat, but I'll probably answer them in the last 15 minutes of this workshop. There will also be a quiz at the end, if you complete the quiz, you will be eligible to win a full suit of Flare merch, so stay tuned for that. But without further ado, let's get on with it. So first of all, let's look at what data we'll be accessing. So we'll be using OpenWeather, which is a public-facing API. You do have to register to use it, but otherwise it is free. The only caveat is that you need to provide an API key with your requests, which you get when you register here. So first of all, let's look at what the basic idea of this weather agency is. We will be writing a smart contract, which will basically facilitate the whole exchange. But other than that, the agency will run truly through user input or through user actions and no actions on our side. There will be two agents involved in this scenario. The first we call the policyholder, and this is the one, the agent that wants to insure their assets or something. The second agent is the insurer, and they're the one that are willing to take on the risk in exchange for a premium. So the way things will work is that the policyholder will first create a policy where they will specify a premium that they are willing to pay and the coverage that they expect in return. They will also specify for what time interval the policy is in effect, and also a loss criterion that determines if the coverage should be paid out to them or not. And in this case, the loss criterion will be whether a minimum temperature has been reached for a certain day. So once the policyholder creates a policy, it is up to an insurer to calculate their risks and take on a policy. If they decide to accept the policy or claim it, they need to deposit the coverage to a smart contract where the policy was created, and they get paid the premium immediately. And then the policy coverage remains with the smart contract until the policy is resolved. So there are three ways a policy is resolved. First of all, if the policy has not been claimed even, and its expiration timestamp is reached, the policy is retired and the premium is paid back to the policy holder. Now, if the policy has been claimed, then there are two scenarios how it can be resolved. The first way it can be resolved is that its expiration timestamp is reached without a proof being provided that a loss has occurred. In that case, the coverage is refunded to the insurer. But if a proof is provided to the policy that a loss has occurred, in this case, that the minimum temperature has been reached, then the policy coverage is paid to the policy holder. Now, who is responsible for providing the proof? Well, no one is compelled to do it, but it is in the interest of the party that would receive the funds to resolve the policy. So in the case of a loss, the policy holder would be the one to bring the proof and resolve the policy that way. And in the case that no loss has occurred, it is in the best interest of the insurer that they expire the policy so that they can get their funds back. In this sense, it is truly decentralized because, all in all, anyone can do it. A random person would be able to resolve a policy, they just wouldn't get anything out of it. But the fact of the matter is that this way of doing things is decentralized. So let me just get a sip of water. So let's now take a look at the API for OpenWeather. And more specifically, the current weather and forecast. So we will be using the Flare data connector to get this data. The Flare data connector allows us to access arbitrary Web2 data and bring that on chain. There are basically three things that we need to provide to the FDC hub or to the FDC protocol so that it can collect the data for us. The first piece of data that we need to provide is the URL of a public API that basically returns a JSON formatted data to us. So in this case, the URL that we will be providing is this one, where we will replace the latitude and longitude with the appropriate values, and I will show which ones in a second, but they are not that important, to be honest. We will also need to give them our API key, and this one we get with the free account if we just go somewhere on here, but I won't show them so that we avoid getting spam on my account. And we will also be providing units being metric, just because to make sure we're on the same page. So yeah, we'll modify this URL and get back a JSON that looks something like this. A word about the JSON API attestation type. The only real limitation, or the two real limitations on what it can do right now, is that the API must be public, or we must be able to provide a key the way we do here. There can't be an intricate protection around the API. That's the first constraint. And the second is that it has to return a JSON with the data in it. So as long as we can get the JSON object back, we're basically good to go. So yeah, let's take a quick look at the JSON response that we get from the OpenWeather API. We get the latitude and longitude of the closest weather station to the coordinates that we provided. And this will be important because in order to specify the policies in a way that we can compare the coordinates, we will need to create a policy containing the coordinates of the closest weather station to the location that we are interested in. Then we get several things back, like what kind of weather it is. For example, here it is ID 803 clouds, and this is contained in another example that we've prepared, but we won't be looking at this today, because what we'll be interested in is the current weather, and specifically where is it? Well, anyways, we will be interested in the minimum temperature. Perhaps this one here is somewhat deprecated. We'll look at a real example in a little while. Cool. So with that, let me first direct you to the Flare Developer Hub. So you can find written guides for Hardhat and Foundry on this site, although the weather insurance example is only available for Hardhat as of yet. And now the second thing, the second site I want to show you is the Flare Hardhat starter. So this is the repository which contains the code for all of these examples, including the weather insurance agency. So what I've done already is I've cloned the repository and then followed the instructions in the README file. So I've run the yarn to install the dependencies. I've created a .env file and populated it with in certain values. So I replaced the private key with my private key, and I've also added the API key for the OpenWeather to my .env file, and we'll be reading the value for the API key from the .env file. Now, let's look at the contract for this example. We only need a single contract. In this case, it is within the contracts weather insurance and mean temp and agency.sol file. The second file is the one that I've mentioned that takes the ID of the weather situation and basically decides whether a loss has occurred using that. Now, right at the top of the file, we have a data transport object. This will come into play in a second, so let's just skip that for now and look at the main contract, so the mean temp agency. It has an array of registered policies and also a mapping from the ID of a policy to the address of the insurer. We need this so we can pay back the coverage if a policy is expired without a proof of loss being provided. But basically, the main struct in this example is the policy. It has the address of the policyholder, which is assigned automatically when policyholder creates the policy. Then it contains the coordinates, which again need to be the coordinates of the closest weather station. Then there are the start and expiration timestamps, so which define the lifetime of a policy. And then there is the minimum temp threshold, which is the threshold value that if the minimum temperature falls below this value, that will constitute a loss. So this is the loss criterion I've mentioned at the start. Then there are the premium and coverage values, which we'll see how they are assigned in a second. And then there's the policy status. The policy status is the enum, which has three possible values. So when a policy is first created, it is unclaimed, and once an insurer claims the policy, it becomes open, and it remains open until it is settled. That is, until it is resolved, expired, or retired, and so then it becomes settled. This is important so that we can check real quick whether a policy is even worth examining or not, because it will be it's a safety measure to ensure that only policies of the right status are accessed at certain steps. And then there's the policy ID, which is assigned automatically when a policy is created. Now, here are a few events. They are omitted at appropriate stages of the workflow and are self-descriptive. But now let's go through those stages. The stages, I've described the stages at the start of the workshop. But yeah, let's just go through them again. So first of all, a policy needs to be created. The policy holder needs to specify the latitude and the longitude of the closest weather station. Then they must provide the start and expiration timestamps for the policy. They need to define what they consider a loss and what coverage they expect in return in case a loss occurs. You might be wondering, where's the premium for the policy? Well, the premium is defined by the value that they pay to the contract. So the first check we do is we check if any ether has been sent to the contract, and if the number is 0, then we just revert, because that's a policy no one would be willing to take. Then we check the validity of the data, of the timestamps, and if everything's fine, we create a new policy and assign the message sender as the policy holder, and declare the premium to be the value that they sent with this transaction. And the ID is taken to be the length of the array of registered policies. So we just increase the ID of the latest policy to 1 by 1. And so we also add the policy to the list of registered policies, and then a policy created event is emitted. Cool. So that's the first step, creating a policy. The next one is claiming the policy. So an insurer sees a policy that they find acceptable, and they perform a claim policy function call on this contract with the ID of the policy that they want to insure. First of all, the policy has to be unclaimed as of yet. Then we check that that the policy has not come into an effect yet, because what we are trying to avoid here is the scenario where a policy would be seconds from expiration or something, and someone would come in to sweep to basically sweep out the premium without taking any risk at all. So that's why we do this. We only allow accepting policies before they come into effect. And then we check that the insurer has paid the proper premium, the proper the proper coverage. And we are not bothered if the coverage is larger than expected, and we are not we aren't returning the value. So it's up to the insurer to ensure that the value they pay equals to the coverage. But we could also implement a refund method here quite easily. Then we set the policy statement to open so that no one can claim it. We update the state. We update the state of the policy to open and declare the sender of the transaction as the insurer for the policy. And only then do we pay the premium to the message sender. And after that, the event is also emitted. But here's an important point. We first update the status of the policy before sending the premium to the insurer. We need to do this so that a malicious actor doesn't send multiple calls to the contract and take out a larger premium that they actually want are willing to pay. So it's very important that the state is updated before any transfer of funds occurs. Now, we're almost to the end of the policy's lifetime here. The last thing to do is to resolve a policy. What we need to do here is, so a policy resolution can be triggered by anyone, but in practice, this would be the party that has the most to gain. What they do, or rather, the policy holder is usually the one that would do this, because this function specifically is designed to return to pay the policy coverage in case of a loss. So what the agent that triggers the policy resolution needs to do is provide an JSON API proof, which also contains data which the policy will compare, and of course the ID of the policy. This is the .proof struct of the JSON API attestation type. So what we do is, first of all, we check that the policy is actually still open, and then we verify the proof. This happens automatically on chain. All we have to do is to get the JSON API verification contract or the auxiliary contract. The JSON API verification contract, and call it verify JSON API on the proof that was provided, and that will verify the proof. Once the proof is deemed valid, we decode the data that we've been sent to a data transport object. This is the one that I've skipped over earlier. So let's talk about it now. A data transport object is just a struct that we would like our data to be encoded as. And I'll explain in a second how we can specify this to the FDC protocol. I mean, how we can specify how data should be encoded. But as you can see, it contains certain fields that can be taken from the JSON at the OpenWeather API. But more on that in a second. So we decode the data. We make sure that the timestamp of the current block is greater than the start timestamp of the policy, which means that the policy has come into an effect. And we also check that the policy has not yet expired. And if it has, we expire the policy. So the policyholder is not incentivized to call this function if a policy has already expired. We also check the coordinates, and this is why it's important that they match the coordinates of the closest weather station, because the longitude and latitude in the data transport object are exactly the ones from the JSON API, which are the coordinates of the closest weather station. And then lastly, we check that the minimum temperature threshold has been exceeded, and so that the loss has occurred. And if a loss has occurred, then we proclaim the policy is settled. We update the state of the policy in the registry. And again, we only transfer the funds to the policy holder once we've updated the state. And in this case, we pay the policy coverage to the policy holder because a loss has occurred. Now let's look at the other two options for a policy to reach the end of its lifetime. The first one that's already been used is expire policy. This one makes sure that the policy is open, that the timestamp of the current block exceeds the expiration timestamp of the policy. And if that is true, the policy is proclaimed as settled, the state is updated, and the policy coverage is refunded to the insurer. And the last option is to retire an unclaimed policy. Basically, no one is incentivized, or rather the policy holder is incentivized to do this if the policy has expired. So what is the criterion for that? Its status is still unclaimed and the current timestamp is greater than the start timestamp of the policy. And if these two conditions are true, the policy status is set to settled, the state is updated, and the premium is refunded to the policy holder. And again, an event is emitted. We have a few auxiliary functions here. The one that's really interesting to us is the ABI signature hack. This function does basically nothing. It only takes a data transport object as a parameter, but that's actually the key and the reason why we have it here. You see, I've mentioned that we need to specify to the FDC how to encode the data that it retrieves from the API, from the website. And there's another thing, there's a step in between, which I'll focus on in a second. But yeah, we basically need to specify how to encode the data it gets back. And we do that by providing the API signature of the object that we want to the FDC. And this function helps us to do that, because in Hardhat, once we have compiled the project, we can go to artifacts, contracts, weather insurance, mintemp_agency.sol, and mintemp_agency JSON. And here we can look for API signature hack. This is one of the functions here. And if we look at its inputs, we can take this object here, which corresponds to the data transport object, and we can just copy and give this to the FDC as one of the parameters, and it will know how to encode the data it gets back. Cool. So let me get a sip of water. There's one more thing to talk about right now, and that is, how can we, after getting back something like that, how can we extract only the things that we're interested in and make them compatible with Solidity, and basically transform them into the data transport object form, which is again something like that. So how do we produce this transformation? And the answer is we use a JQ filter. So let's go to the JQ Playground website, and let's paste in the example JSON. And what this allows us to do is to, for example, get latitude by doing something like that. Of course, the thing that I've given it is not actually a valid JSON, which is very cool. Let's try to copy this one and hope this one works better. Yeah, and as you can see, we got our latitude by just simply calling the lat field. But there is a small problem here, and that is that what we get back is a floating point number, and Solidity doesn't do with floating point numbers. So what is the solution? Well, we multiply it by a large number, and then we'll be made aware, or we'll be aware that we're operating with multiples of a number. And another thing that we'll also have to do